Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky. Beyond Lanikea, unveiling the Milky Way's place in a greater cosmic web. The Milky Way, the galaxy we call home, is more than just a swirling collection of stars, gas, and dust. It is part of a much grander cosmic structure. For a long time, astronomers believed our galaxy resided in a region known as the Lanikea supercluster, a vast network of galaxies stretching across hundreds of millions of light years. However, recent research suggests that Lanikea might itself be a smaller piece of an even larger structure, potentially opening up new dimensions in our understanding of the universe. This newly discovered region is known as the Shapley concentration, a titanic basin of attraction that has captured the attention of scientists trying to map the true shape and scale of the cosmos. If someone were to draw a cosmic address for the Earth, they would begin with our planet, which is part of the solar system, nestled within the spiral arms of the Milky Way galaxy. The Milky Way itself is a member of the local group, a collection of nearby galaxies, and this local group is part of the Virgo cluster. The Virgo cluster, in turn, resides within the much larger Virgo supercluster, which is itself a part of the colossal Lanikea supercluster. It's a bit like nesting dolls, with each layer of the universe fitting within a larger one. And now, astronomers are beginning to believe that Lanikea, massive as it is, might be part of an even larger structure, the Shapley concentration. The Shapley concentration is a name that may not sound familiar to many, but it represents a region of space loaded with mass, a gravitational basin of attraction that tugs on everything around it, including entire clusters of galaxies. Discovered through deep sky surveys, this region contains numerous galaxy clusters and groups, all dominated by gravity, which attracts both visible galaxies and invisible dark matter. As with any massive object, its gravitational pull influences the motions of everything in its vicinity. The sheer scale of the Shapley concentration places it among the greatest concentrations of matter in the known universe. Astronomers are keen to learn more about such cosmic basins, and they are working to map them with greater precision. By understanding how these enormous gravitational regions are distributed, researchers hope to develop a clearer picture of the universe's largest structures. One such group of scientists, led by our Brent Tully from the University of Hawaii, has been at the forefront of this effort. Their work has revealed that the universe is far from a random scatter of galaxies. Instead, it is a vast web where galaxies lie along filamentous structures, clustering at nodes where gravitational forces pull them together. Tully compares this cosmic arrangement to watersheds on Earth, where water flows through basins and valleys. Similarly, galaxies move within these cosmic basins of attraction, directed by gravity toward dense regions of mass like the Shapley concentration. Tully's team, called Cosmic Flows, focuses on measuring the motions of around 56,000 galaxies, studying their trajectories through space. Their observations suggest that the cosmic web might be more complex and interconnected than previously thought. While we have long known that we reside in the Lanikea supercluster, which spans some 500 million light-years, The motions of galaxies in our neighborhood hint at the presence of a larger structure pulling everything toward it. This larger structure could very well be the Shapley concentration, a massive attractor that could be up to 10 times the size of Lanikea. In comparison, the Shapley concentration has roughly half the volume of the Great Wall, a massive filament of galaxies stretching across 1.4 billion light-years, the largest known structure in the universe. The Shapley concentration is no recent discovery. It was first observed in the 1930s by the renowned astronomer Harlow Shapley, who noticed a peculiar cloud of galaxies in the constellation Centaurus. This cluster of galaxies, located in the direction of motion of our own local group of galaxies, intrigued scientists, who began to suspect it might be influencing the movement of the Milky Way and its neighboring galaxies. This suspicion is supported by recent surveys that suggest our entire Virgo supercluster, along with the local group in Milky Way, is moving toward the Shapley concentration. The gravitational pull of this distant region is, it seems, shaping the cosmic flow in our corner of the universe. Astronomers continue to explore this fascinating discovery, using surveys to confirm the motion of galaxies toward the Shapley concentration. The research conducted by Tully and his colleagues is part of a broader effort to explore the ever-expanding boundaries of the universe, and to understand how these massive structures came to be. The gravitational forces that define cosmic basins of attraction like the Shapley concentration have been at work since the dawn of the universe, 13.8 billion years ago. In the aftermath of the Big Bang, the universe was in a state of hot, dense chaos. As it expanded and cooled, subtle fluctuations in the density of matter began to take shape. These tiny variations would eventually become the seeds of galaxies, galaxy clusters, and the vast superclusters that we observe today. The cosmic web that Tully and others are mapping was woven from these early fluctuations. Over time, gravity pulled galaxies together into clusters and superclusters, forming the large-scale structure of the universe. The Shapley concentration represents one of the largest and most significant of these structures, and its discovery could fundamentally reshape our understanding of the cosmos. Current cosmological models, while successful in many respects, struggle to explain the existence of such massive basins of attraction. As Ehsan Korkci, a member of Tully's team, pointed out, our cosmic surveys may not yet be large enough to map the full extent of these immense basins. In other words, we are still peering at the universe through a limited lens, and there is much more out there waiting to be discovered. The sheer scale of these discoveries is mind-boggling. In addition to the Shapley concentration, other superclusters, such as the Sloan Great Wall, have been revealed by galaxy redshift surveys like the 2DF Galaxy Redshift Survey. These surveys offer a glimpse into the intricate tapestry of the universe's large-scale structure, revealing enormous walls, filaments, and voids that stretch across billions of light-years. These are the skeletons of the universe, the framework upon which everything else is built. And at the heart of it all is gravity, the fundamental force that governs the behavior of galaxies, clusters, and superclusters alike. Gravity is the engine driving the motion of galaxies within cosmic basins of attraction. The more mass a region has, the stronger its gravitational pull, and the more it influences the motion of galaxies around it. The Shapley concentration, with its immense mass, exerts a powerful gravitational force that tugs on galaxies far and wide. By studying the motion of galaxies, astronomers can map the extent of these basins of attraction and determine how they are distributed throughout the universe. To do this, Tully and his team rely on a variety of measurements, including redshift surveys, which provide information about the velocity of galaxies along our line of sight. They also measure something called peculiar velocity, which refers to the difference between a galaxy's actual velocity and the expected velocity based on the expansion of the universe, known as the Hubble flow. By combining these measurements, astronomers can build detailed 3D maps of the universe, charting the position and motion of galaxies with incredible precision. These maps are not just static images, they are dynamic representations of a universe in motion. The galaxies within cosmic basins of attraction are constantly moving, drawn together by the inexorable pull of gravity. As Tully and his team refine their maps, they are uncovering new insights into the distribution of matter in the universe, including the elusive dark matter that makes up much of the universe's mass. In the coming years, as more advanced telescopes and surveys come online, our understanding of these colossal structures will continue to grow. The discovery that the Milky Way might be part of a larger structure than Lanikea is just the beginning. As we peer deeper into the cosmos, we may find that our universe is more interconnected and more complex than we ever imagined. The Shapley concentration and other basins of attraction are but pieces of a grand cosmic puzzle, and it is up to the astronomers of today and tomorrow to fit them together and reveal the true shape of the universe we call home.